The purpose of this class is to gain a foundation behind the ideas of SPC that are utilized in our product WinSPC. This is the course agenda for SPC Fundamentals. We're going to be covering an introduction to SPC. We'll then be covering the 7 SPC tools with an overview. We'll then go ahead and have a detailed section for each of the different tools, including the check sheet, the Pareto chart, cause and effect diagram, control charts, histograms, process capability studies, and scatter diagrams. We're then going to discuss which SPC tools you should use during your process improvements and implementations. And then we'll discuss how WinSPC can be used with your SPC's initiatives. So first, what is SPC? SPC stands for Statistical Process Control, and it is a method for achieving quality control in a manufacturing environment. There are a core set of 7 tools for use with SPC. These are intended to be used for improving your process, for monitoring and controlling ongoing process, and the implementation of SPC can have the effect of moving your organization, your manufacturing process, from a detection model where you're reacting to problems as they occur to a prevention model where you're proactively preventing problems from occurring in the first place. Thus, you'll be reducing the cost of producing non-conforming parts, as you'll have caught problems before they will have arisen, and you'll reduce the cost resulting from finding these costs, as you will have less need to detect. You will have less of a need for 100% inspection, and you'll have less need to repair and spend time towards fixing problems after they have already come up. This slide has a Venn diagram on it that covers the 7 SPC tools, and it organizes them based on whether or not they fall under the category of problem identification versus problem analysis. So you have the check sheet, which is the fundamental tool of evidence that we're going to be using for SPC, and that falls squarely in the category of problem identification. It lets you know or identify with evidence that you have a problem in the first place. Pareto charts, which are very tightly tied to check sheets, begin your process of analysis. You'll see how that ties in when we cover that. The cause and effect diagram both allows us to see what the underlying root cause of a problem is, as well as begin the process of actually analyzing ways of fixing it using brainstorming techniques. Histograms fall squarely in the problem analysis category, where we can actually use concepts of the shape of the histogram and the properties of normal distribution in the bell curve to identify that. We have scatter diagrams, which we can use to correlate different variables, whether or not there's a relationship, and if so, what kind, and that allows us to analyze the relationship. We have process capability analysis, which gives us a grade on how that information, how our process has either improved or degraded now versus previously, and how it actually is right now, how our process is actually behaving. And then we have also control charts, where we are able to, in real time, view what the state of our process currently is. So the first tool that we're going to cover is the check sheet. So what is a check sheet? It's a simple, user-friendly form of collecting data for a period of time. It's literally a piece of paper that you record defects over the course of some period of time, be it a day or a week or a month. So in this particular slide, we have an example where you have a pencil manufacturer who's been collecting defect data for the past week or for a given week. You can see that this pencil manufacturer had a number of different defect types that were available or that were occurring. You had on 213, there was lots of broken leads, you had bent pencils, an eraser, pencil assembly that held the eraser to the pencil was loose. You could see that it got even worse for some of these defect types on the 14th. Things seemed to clear up a little bit on the 15th. It was really bad on the 16th where there was defects all over the place, and then it sort of calmed down again on the 17th. So you see that there are defects across the entire week, and now you actually have evidence that something is actually wrong rather than just seeing a defective unit and not tracking it and not putting a time stamp on it of some kind. So what are some of the advantages of using a check sheet? Well, it's very simple to use and it's easy to construct. Anybody can really understand a check sheet, assuming they have any idea about your manufacturing process. And it's very useful for data collection for an improvement project. It is evidence for an initiative to begin quality. I have a problem. I have defects. Let's start going and putting some effort into actually improving our process so that these defects no longer occur. What's something that's really important about check sheets, you have to make sure that you have a separate check sheet for each project. You can't really mix and match these. We're going to see when we talk about some other tools later on, including the histograms and the control charts. If you start mixing different processes together or different initiatives together, your data is not necessarily going to have value to you because it's going to be coming from distinct sources. The next SPC tool that we're going to discuss is the Pareto chart, which is highly tied to the data recorded via check sheets. But first we're going to go ahead and do a little bit of history about the Pareto chart. Vilfred Pareto was an Italian economist in the 1800s. He studied wealth distribution, among other things, in Italy. He found that 80% of the wealth in Italy was concentrated with just 20% of the population. This observation was echoed by Joseph Duran in the 1940s, and he applied this idea to quality. He determined that 80% of the problems, the quality issues that were occurring, the source was from only 20% of the causes. This idea is known as the 80-20 rule and has also been dubbed the Pareto rule, as in honor of Vilfred Pareto, who came up with this first observation. Other applications where the Pareto rule comes into play, 80% of most product cost is due to 20% of the raw material. In many companies, 80% of sales is due to 20% of customers. Once you have this knowledge that in normal situations, 80% of your results is from 20% of your causes, the wise man would go and make sure to find out what that 20% of the causes are to get the best results for your effort. So now that we know what the basis of the 80-20 rule or the Pareto principle is, what is a Pareto chart? A Pareto chart is a combination chart that shows both a bar chart for the percentage frequency of each cause as well as a cumulative curve or a cumulative frequency curve of all of those causes combined. Once you have a Pareto chart, you can use it to prioritize the problems that occur within your process, ultimately allowing you to separate the vital few causes from the trivial many. You have many different things that could theoretically go wrong in any given process. The best use of resources is to find out where 80% of the problems are, and therefore we will be focusing by result on only 20% of the causes, and you will then be able to focus your energies more wisely. So here's an example of a check sheet and how you go about taking the data from a check sheet and putting it into a Pareto chart. So you have a pencil manufacturer. A process improvement team wants to prioritize the types of defects found in pencils. They have collected data about the defects for the last week, so we're going to expand upon the example we covered a little earlier. This slide shows the data for defects found in 1 week. Now our goal is to construct a Pareto chart based on the data found in this check sheet. The next thing you need to do after sorting the data into descending order is to calculate the percentage frequency of each of the defects relative to the total number of defects that you have for your entire count of defects. So in this case, the most common defect type that we have within our system is broken leads at 27 total. The next most frequent is loose assembly. After that is bent pencils. Then we have aesthetic problems. Then we have other problems that don't quite fit into any of the other categories. As they're sorted now, you can then go about calculating the percent frequency out of a total of 73 count. You have 27 out of 73 times 100 gives you 37%. That's for broken leads. For assembly loose, you can go ahead and take 16, divide that by 73, multiply it by 100, and get 21.9%. You continue to do the calculation for each one of these different defect types. After you're done calculating all of the individual percent frequencies, the next thing you're going to do is you're going to add all of the frequencies together for a cumulative frequency that will eventually be plotted on the chart as a curve. The first and most common type of defect is going to be at your top, and that equals your same as your percentage, 37% in this case. For the next node in the curve, you're going to have your 21.9% from your assembly loose. You're going to add that to your 37% from your broken leads. That totals out to be 58.9%. You're going to go for the next one, which in this case is bent pencils. You're going to add that 19.2% individual frequency. You're going to add that to your previous total, which gives you a total of 78.1%. You keep doing this until you've completed adding all of your cumulative frequencies together. A quick check on your math to make sure that you've added everything properly. If your cumulative frequency doesn't add up to about 100%, you've probably calculated your percentages wrong, or you may have added them together wrong, and you need to go back and do it again. By organizing it in this way, you will now be focusing on the vital few causes rather than the trivial many. If you were to enter this data into WinSPC's data collection mode, this is what the Pareto chart would look like within the software. So now that you've seen how you could construct a Pareto chart by count or by frequency, the next step is to add the cost dimension to it. You can rerun a Pareto chart not just by the straight count or occurrence of certain items, but by adding a cost associated to each defect type, you can add even more value to what you should be focusing on, because cost ultimately is what you're trying to reduce by doing a quality initiative. You want to reduce costs and you want to focus your quality dollars to be able to focus on just that vital few that's costing your process the most amount of either money or man hours or any sort of quantifiable value where you want to go ahead and reduce those defects. Not all attributes are created equal. Not all defects are created equal. So if you do have a cost that can be associated with your different defect types, either in terms of money or man hours, you can construct a Pareto chart that is sorted by cost. So we can take the exact same data that we had previously, where we were having a company that manufactured pencils, and they had the same defect types at the same actual count frequency: broken leads 27, loose assembly 16, bent pencils 14, aesthetic problems 13, other 3. We can actually assign a cost in this particular instance. Broken leads are worth 60 cents per defect, assembly loose 50 cents per defect, bent pencils 80 cents per defect, aesthetic problems 20%, or excuse me, 20 cents per defect, and other problems are given a sort of generic 20 cents per defect. So when you're doing a Pareto by cost, you have to shift your order a little bit. The first thing that you need to do is you must calculate the cost each defect type has within your process from your check sheet. So you need to count the total cost for broken leads. In this case, it's 27 instances at 60 cents per defect equals a total of $16.20 worth of cost of defect in actual total cents. And you would do this for each step. Assembly loose, 16 times 50 is 800 or $8. Bent pencils cost you 80 cents. In this case, bent pencils are obviously a more costly problem than just having a loose eraser assembly. And then you have aesthetic problems totaling $2.60 and other problems causing just 60 cents. So now that you have the actual costs of each one of these different defect types, you need to again sort the defects in descending order, but instead of doing it by count, now you're just going to use the dollar value. So the most expensive defect, the one that's costing us the most money, is the broken leads. Then next is the bent pencils, then the assembly loose, then the aesthetic problems, and then everything else. Just like we did with the count, we need to calculate a total cost of all defects combined. In this case, it equals $38.60. Then, just like we did with the Pareto by count, we calculate a percentage frequency for each individual defect type, and this is going to be against the total cost. So it's $16.20 divided by $38.60 equals a 42% frequency. Same thing with the bent pencils. $11.20 divided by 38.60 is going to give us 29%. We do this for each one of the defect types. Once you have the percentage frequency, you can go back and actually do the cumulative frequency, starting at 42, which is the first value, the one for broken leads. Then you add the 29% that comes from the bent pencils to the 42% of the broken leads. That's equals 71. Then you have the loose assemblies. It's going to give you 20.7 plus 71 from the previous summation. That gives you 91%. You just add all of them together, and you should get a value that's really, really close to 100% total when you're done adding up all of your values. Now, it may be off by a few fractions of a percent due to rounding errors from your calculators. Don't worry about that. It just should be in the ballpark of around 100%. So now that you have sorted your percent frequency of your individual values in descending order, and you've calculated a cumulative frequency, you can plot your bar chart for your percent frequency of the individual defect types, then plot your curve for your cumulative frequency superimposed over the bar chart, draw a line from 80% over until it touches or until it intersects your curve for your cumulative percentage, and drop the line down to see what falls inside of the box you've just drawn. And in this case, we have the broken leads and the bent pencils as the 80% of our problems, and that is in contrast to the by count, where we actually had 3 items falling within our 80% area, and they were even in a different order. Loose assembly would have fallen in if we hadn't taken cost into consideration. Cost has actually added visibility to this Pareto chart by allowing us to focus on what is truly the most expensive defects to our process. In this case, it happens to be just 2 items rather than focusing without a Pareto chart where you may be all over the place trying to put your energies into solving all 5 problems that you have recorded on your check sheet. WinSPC does support the use of costs or weights associated with your different defect types, and this is what your chart would look like with the same information inside of data collection within WinSPC. Furthermore, WinSPC can actually give you visibility at the same time, allowing you to compare a Pareto chart by cost with a Pareto chart by count. So you can actually do a comparison of, okay, certain things may be costing me more, but I'm still getting a lot of aesthetic problems. Even though I have assigned a low cost to it, maybe I still want to focus on it. But at least I can now justify focusing on just a vital few set of problems because due to the Pareto rule or Pareto principle and the 80-20 rule, that should be caused by 20% of my causes. On this slide, you can see what I would refer to as a more realistic Pareto chart, something that you might see in a more realistic complex manufacturing environment. You have lots of different defect types, and it really becomes a lot more important to be able to prioritize which of these defects you should put your resources against. The examples we were using earlier was great for demonstration purposes, but this really illustrates where I have so many problems in this particular example for a Pareto chart for defects in TVs that I'd go crazy if I tried to find just a couple of things that I need to put my money on. But in this case, I can focus my quality dollars using evidence from my check sheet to say, look, the Pareto chart, the 80-20 principle allows me to say that, yep, these are the problems that are costing me the most. These are the problems that are either most frequent, and I can go ahead and thereby get the best results from my quality initiative. Once you have that, you will find that you're going to run another Pareto chart after you've done your quality initiative, and hopefully, if your initiative was successful, your items that fell into your Pareto 80% area initially may no longer be in that position. Maybe they'll fall to the edge of the list. Maybe you'll completely get rid of those defect types altogether. However, when you run that next Pareto chart, you have to run the 80-20% rule again, and you'll have a new set of items that are going to fall within your 80-20 area. If you consider using these Pareto charts as part of a continuous improvement initiative, where you're constantly trying to better your process and your product, then the way you look at these Pareto charts is as sort of a living document. You run a before, you run an after, you have a new set of items that are in your 80-20 area. Now you go and solve the new items. The next time you run your quality initiative, hopefully nothing new has cropped up, but if it did, you can take care of that. And if not, you can go ahead and start focusing on the next set of 80-20. And through this process and through this mentality, you will eventually be able to get into a situation where you are proactively preventing problems and customer complaints rather than reacting to fires that come up because the quality of your product isn't as high as it could be. So what are some of the advantages of using the Pareto chart? Well, it helps you prioritize with evidence what items you should be putting your energy towards fixing or towards addressing. And you rely on the Pareto principle to guide you in this initiative. And it enables you to focus on the vital few, because people are really good at focusing on just a few things and making decisions amongst a few different items. Humans are not quite as good taking into account many multiple variables and trying to decide how to handle it. Now, the disadvantages of a Pareto chart, and this sort of was mentioned in the previous slide, this is just a snapshot of your process at a given time. You want to take a Pareto chart before quality initiative, decide where you want to put your energies towards improvement, And then you have to take another Pareto chart afterwards to see if there were any results and do a comparison. And then if you didn't get the expected results, you have to do it again. If you did get the expected results, then you maybe want to start focusing on a different issue. But ultimately, you have to keep running these Pareto charts as they will reflect different things over time. You keep taking a snapshot of your process. So this is not intended to be a tool for ongoing processes. This is not a real-time tool that you can use. So here's some useful tips regarding Pareto charts. You definitely want to compare Pareto charts based on counts and costs for prioritization. While certainly the by cost is the most tempting way to approach an improvement process, and definitely that makes a lot of sense in most instances, there's other things you may want to consider. Let's go back to the example of the pencil. Sure, maybe you can still ship your pencils if there's some scratches on the paint, and you can't ship anything at all if the eraser assembly is loose. But at the same time, do you really want to ship products to your customers and they all have scratches on them? It may not cost you in that you can still sell it, but you're going to get a lot of customer complaints, and customers may be dissatisfied and maybe try to get another pencil manufacturer who produces less scratches. So you really have to weigh the costs and benefits of the by strict cost versus by count, depending on how your product is used and how you expect that this is going to affect your product as a whole. To monitor progress, you want to do a Pareto analysis before and after process improvements, and that's just so that you have evidence to say, yep, either this worked, whatever initiative I took to improve something worked, or it didn't work, or something else came up in the meantime that's even more pressing than what I had been focusing up until this point. So you definitely want to have this a Pareto chart before and after any given quality initiative. So here's an example of a Pareto chart. So in this example, a process improvement team wants to prioritize the type of defects found in radios. They have collected the defect data for the past month. Data for the type of defects found in a radio are listed in the check sheet below. In this case, just like we did in the example that we did together, we have amplifier problems, assembly loose, speaker output, scratches on the cover, loose knobs, packaging issues. You have a count for each one of these. You have a cost for each one of these. Your job is to construct two Pareto charts. One Pareto chart should be for the count, and an additional Pareto chart should be for the cost of defects. Here's the solution for the Pareto chart construction, both by count and by cost. So we can see here, just like we saw in the example, the first step to doing a Pareto chart by count is to sort the defect types in descending order by count. The next thing we need to do is calculate the percentage frequency of each one of the different defect types. Next, we would want to calculate the total number of defects overall. In this case, the addition of 60 for assembly loose, 50 for amplifier problems, 40 for packaging issues, 30 for scratches on the cover, 20 for the speaker output, and 10 for the loose knobs. Add that together and you have a total of 210 defects. You then calculate your percentage frequency from your total for each one of the defect types. So in this case, it would be 60 out of 210 equals 28.6. 50 out of 210 equals 23.8. 40 out of 210 equals 19. 30 out of 210 is 14.3, 20 out of 210 is 9.5, and 10 out of 210 is 4.8. To get the percentage in whole numbers, you would multiply each one of those values by 100. The next thing you do is you calculate the cumulative frequency. So first thing would be 28.6, that's the assembly loose. Then you'd add 23.8 from the amplifier problems to the cumulative frequency to give you a total of 52.4. Then you'd add the packaging issues as 19% to give you a total, and you sum that with 52.4 to get 71.4%. Take the 14.3% of the scratches on the cover and add that to the cumulative frequency, give you a total of 85.7%. You take the 9.5% from the speaker output, add that to the 85.7% to give you a total of 95.2%. And then you have the 4.8% from the loose knobs to add to the 95.2 cumulative frequency, and that should give you 100%. When you add this together yourself, your calculator may round this slightly differently. You want to get something that's close to 100%, with a margin of error of usually about 0.5%. If you're off by more than that, you've probably done your percentages wrong, and you should probably do it over again. The next thing you need to do is you want to plot a bar representation, a bar chart for each one of the different defect types, starting with the highest and moving on to the lowest. So the first one's assembly loose, then you want amplifier problems, then you want packaging issues, then you want scratches on the cover, then you want the speaker output, and then you want the loose knobs. After you've plotted the bar chart, you can then plot the curve chart. That's the curve of the cumulative frequency. When you do that, you will have a curve represented for each point where you've added a new item or a new defect type to the total cumulative frequency. Then you want to draw a line from the 80% from the percent frequency, and when that intersects your curve for cumulative frequency, drop a line vertically down. Everything inside the box that you've just drawn, all of the different defect types within that box, are your 80% of your problems that, according to the Pareto rule, the 80-20 rule, should be caused by 20% of your problems. So next we're going to do the Pareto by cost. With Pareto by cost, it is very important to first calculate out the total cost of each defect, taking into account the cost per defect values. So that's the first thing you need to do. So in this case, for amplifier problems, it's $750 total because it's 50 times 15. Assembly loose is 60 times 20 for a total of $1,200. Next is speaker output, which is $20 20 count times $15 equals $300. Then you have scratches on the cover, which is 30, cost of $2 per scratch, that's a total of $60. Then loose knobs, which is 10 count with $10 per defect, that total of $100. And finally, packaging issues, you have a count of 40. The cost of each packaging issue is $5 and gives you a total of $200 for your cost, and that's the cost for each one of the individual defect types. Now you're going to go ahead and arrange the defect types in descending order by cost. So you only take into account the cost in this case. So the first one's going to be the assembly loose, then the amplifier problems, then speaker output, then packaging issues, then loose knobs, and finally scratches on the cover. Now you also want to calculate the total number of costs, your total cost for all defects recorded. In this case, that would be $2,610. The next step is to calculate the percent frequency. That is, again, your cost for an individual defect type divided by your total cost. So the first one would be 1,200 divided by 2,610 for a percent frequency of 46%. Next one is 750 for amplifier problems divided by 2,610 to give you a 28.7% cumulative, percent frequency. Next would be the speaker output, 300 out of 2,610 for 11.5%, 200 for packaging issues divided by 2,610 for 7.7%. Loose knobs would be 100 out of 2,610 for 3.8%. And finally, $60 divided by $2,610 to give you 2.3%. The next step is that you calculate the cumulative frequency just like you did for the by count. The first one is your first value, which is 46% for assembly loose. Then when you add in amplifier problems, it's 28.7% plus 46% to give you a total of 74.7%. The next one is the speaker output for $300 or 11.5%. Add that to the 74.7% to give you a total of 86.2%. Next is the 7.7% of cost from the packaging issues, and you add that to the 86.2% from the cumulative frequency to give you a total of 93.9% cumulative frequency. Loose knobs, 3.8%. Add that to the 93.9% from the cumulative frequency for a total of 97.7%. And finally, you have the scratches on the cover of 2.3%, and that gives you, add that to the 97.7% from before, which gives you a grand total of 100% cumulative frequency. You should always get about 100% for cumulative frequency, no matter if you do this by count or by cost. The next thing you're going to do is you're going to go ahead and plot the bar chart for the percentage frequency of cost for each one of the different defect types. In this case, assembly loose, then amplifier problems, then speaker output, then packaging issues, then loose knobs, finally scratches on the cover. Then you're going to go ahead and plot your curve for cumulative frequency for each one of the different points, for each one of the different additions that you've done for each defect type. You start out with the assembly loose, which is at 48%, then the amplifier problems, which is around 74.7%, so on and so forth. You then go ahead and draw where that 80%, you're going to take 80% frequency and you're going to draw the line across the chart until it intersects with the cumulative frequency curve. And then you want to drop a vertical line down when that intersection occurs. Everything inside of that box is your 80% of your cost caused by 20% of your causes. So in this case, it's assembly loose and amplifier problems, as opposed to in the by count where you had 3 items, assembly loose, amplifier problems, and packaging issues. So if you take into account the cost factor, then your focus becomes a lot more narrow. You're more concerned now with the loose assembly and the amplifier problems, as that is what is costing you the most. So that pretty much concludes the discussion on Pareto charts. Next, we're going to be covering the cause and effect diagram. So the next SPC tool that we're going to be talking about is going to be the cause and effect diagram. So cause and effect diagrams allow you to start analyzing your problem. It's still in the problem identification because you're not necessarily knowing what the problem actually is yet, but at least it's going to start sending you hopefully in the right direction. Cause and effect diagram primarily uses brainstorming techniques to identify possible causes for a problem, also known as an Ishikawa diagram or a fishbone diagram. The way these cause and effect diagrams are structured is that you have the effect, the result of the problem, placed on the right side, and the bone and the branches of the bone, but the bone and the causes on the left. And the bones are categorized. You have 4 major branches. To the left side is the 4 M's: man, method, machine, and material. Some people also include some other things like environment, but in general, when you're talking about processes that you can control, environment's usually not something that you can. That's something that would probably fall under one of the other 4 M's. So what are the steps for creating a cause and effect diagram in your environment? Well, step 1 is to form a team involving all people relevant to the problem. And I want to stress on all people relevant to the problem because it's not necessarily going to help you to bring in people who have no relationship to the underlying problem when you're dealing with these brainstorming sessions. It doesn't help to bring in some supervisor from a different division if they have no experience in this issue. Yet at the same time, you may actually want to bring in your janitorial staff if they're cleaning up afterwards, and you need to figure out maybe they can see something from your process that maybe your operators or your engineers didn't see. So make sure to get everyone that's necessary that has relevance to whatever problems that you're addressing. Step 2 is to brainstorm and list down all possible causes for a problem. And again, I'm going to stress on all here. Even if the possible causes are absurd, they're beyond reason, they're so unrealistic that you'd never actually be a cause that could potentially occur. Because this is just sort of a brainstorming session, write it down. Even in the extreme form, if it's not realistic, there may yet be truth, a grain of truth in even the extreme example. The third step for creating a cause and effect diagram is to arrange the causes and subcauses under the 4 M's. That's man, method, machine, and material. You're going to find as you go through this that there's going to be some potential for either redundancy or potential to list one particular cause in 2 different categories, man or method, or man or machine, or material machine, and it could be sort of dubious. Do the best that you can to try to organize it. You will probably start seeing that there's going to be a pattern as far as where you need to focus on once you start putting down some of these causes. After you've categorized the different subcauses, go ahead and have the team members rank the different causes and as to their likelihood of being the actual cause for the result or for the problem. Finally, the top 3 causes should be listed on the fishbone diagram. So in this particular example, the problem that we have, or the result, is variation in paint thickness, and that's to the right. That's the head of the fish in the fishbone diagram. To the left, we have our 4 M's: method, man, material, and machine. And we have some potential causes that have already been listed for us. In this case, for method, we have unclear instructions, a non-defined workflow. For man, untrained operator, new supervisor. For material, you have inconsistent thickness because of the paint quality. Therefore, you get variation in paint thickness. Then you could have material is the surface is greasy or the surface is unclean. Therefore, you're going to get variation in paint thickness. The machine, the nozzle size could be wrong or not properly calibrated. The pressure is either too low or too high, and that could be a setting issue. So these are different causes that may have come up during a brainstorming session, and they go ahead and get placed onto the Ishikawa diagram. So for a cause and effect diagram, what are some of the advantages and disadvantages? Well, advantages include it's useful for initial brainstormings when you're first trying to figure out what could be going on, because everyone thinks they might know what might be happening, but without having a good brainstorming session and bouncing some ideas off people in your brainstorming team, you don't necessarily have all the facts. So it's a great way to start bouncing ideas off of each other to get at whatever your core issue underlying is. Also, using the inputs from the team helps you list ideas and categorize things that you may not have even considered. Disadvantages for the Ishikawa diagram tend to be that the results may be way, way too simplistic or way, way too detailed. Sometimes in a manufacturing process, the problem is a legitimately difficult engineering technical problem that needs to be solved. On the other side, sometimes it's a almost silly solution to a problem, but it's just something that maybe people were not empowered to implement. So the truth tends to fall more often than not somewhere in the middle, where it's something that isn't as easy as flipping a switch. On the other side, it's not something as difficult as re-engineering your entire product. But that's why it's really good to have a well-rounded brainstorming group to help temper the potential responses or causes for your result. Now, there's some useful tips here for your construction of both the team, the brainstorming team, as well as the Ishikawa diagram itself. First off, you want to update the fishbone diagram with new ideas, even after it's been constructed. An Ishikawa diagram is a brainstorming tool. You shouldn't be using this as sort of a dead document. You do it once. These are the only possible things it could ever be, because that's just not true. There are still things you may not have considered. There may be people who weren't part of the meeting who know exactly what the cause is of your problem, or at least thinks that they know. Go ahead and if you want to have more interaction from your organization, post your Ishikawa diagram somewhere that's accessible, maybe in the lunchroom, so let people actually look at this and be able to change it over time and add new items, and look at it periodically to see if somebody's come up with some new possible ideas as to what is the cause of a given problem. During the brainstorming session, encourage active participation from all team members. Well, just because somebody is really loud does not necessarily mean they are correct. It just means that they're loud. It is your job as somebody who is going to be presumably assembling brainstorming sessions to help moderate a given situation, to both temper those who would be try to perhaps hijack a given brainstorming session, and at the same time encourage people who are more quiet to express their ideas. Quiet people tend to, not speak up in group environments. Maybe you either have to get at the ideas of the more quiet people in the room by asking them after the session itself, or just encouraging a response where they may not have volunteered one. It tends to be, just because somebody is quiet doesn't mean they don't have an idea. It just means they're not the type of person who maybe wants to speak up. So it is really important to both temper those who may be particularly vocal, but at the same time try to coax ideas out of those who may be a little bit more quiet within a meeting. Because if you added them to the meeting, hopefully they have some insight on the situation in the first place.